Hello and welcome to Sleep Science Space. Tonight we gently descend into the ancient and remarkable realm of geology, the long memory of Earth preserved quietly within stone. Long before names were given to stars, before oceans knew their edges, our planet was already alive with motion. Mountains lifted themselves skyward, only to be worn down again. Seas appeared vanished and returned in new forms. Entire continents drifted slowly across glowing oceans of molten rock guided by forces far deeper than the surface we know today. The ground beneath you is older than imagination can easily hold, and yet it is not still. It continues to move, to shift, to breathe in its own deep rhythm. This is the story of geology, a story written not in moments, but in millions of years. A story shaped by fire and water, by pressure and patience, by creation and collapse unfolding far beyond human time. Beneath every step you take, inside every small stone, lie echoes of ancient volcanoes, advancing glaciers, and stars that lived and died before Earth was young. If you enjoy these calm journeys through science and time, you're welcome to subscribe, or leave a quiet thought below. It helps others find their way here as well, one resting mind at a time. But for now, simply breathe. Let your body soften. Let the ancient earth support your thoughts as we begin. The earth's crust is far thinner than most people imagine. If our planet were reduced to the size of an apple, the crust, the solid surface where all life exists, would be no thicker than the apple's skin. This idea can feel unsettling at first, but it is true. The continents and ocean floors together form a layer that averages only about 30 kilometers beneath land and less than 10 beneath the oceans. Below this fragile shell lies the mantle, a vast region of hot, slowly flowing rock that makes up most of Earth's mass and volume. The crust rests upon it like delicate rafts carried by deep currents through a process known as plate tectonics. Mountains, valleys, and deep ocean trenches are merely subtle wrinkles on the surface of an enormous living sphere of stone. Everything familiar, every forest, city, and sea exists on this incredibly thin outer layer, floating atop a world that remains powerful, dynamic, and unseen. Granite. One of the hardest and most enduring rocks we know was once fluid and alive with heat. Deep within the crust, molten magma gathered in vast hidden chambers, moving slowly like rivers of fire. Over immense spans of time, this molten material cooled and crystallized, forming the speckled stone that now anchors mountain ranges across the world. Each crystal of quartz and feldspar within granite once glowed in molten light before locking into place forever. When your hand rests on a granite surface, you are touching the frozen remains of that ancient movement, heat transformed into solidity. Landscapes such as Yosemite's towering cliffs or the Scottish Highlands owe their form to granite that rose from below and hardened in silence. Granite carries the planet's patience within it. It reminds us that what appears solid and unchanging today was once fluid, luminous, and alive beneath immense pressure, slowly becoming something enduring. Diamonds, too, tell a story of extremes. Most form deep within the mantle, where carbon is subjected to extraordinary heat and pressure over billions of years. Yet, under the right conditions, diamonds can crystallize with astonishing speed, forming in moments when nature aligns pressure, temperature, and time just right. Carbon atoms snap into perfect structures, arranging themselves into one of the hardest substances known. Whether formed slowly across eons or rapidly in rare events, every diamond is a message from deep within the earth, carrying the record of forces strong enough to reshape matter itself. But nature does not always move slowly. Under the most extreme conditions, carbon can transform almost instantly. When pressure becomes overwhelming and heat rises beyond anything humans can sustain, ordinary carbon atoms can snap into perfect alignment, becoming diamond in a geological blink. These rare moments happen deep beneath the surface, miles below our feet, where temperatures burn hotter than molten metal and pressure crushes matter into new forms. When powerful volcanic eruptions tear open pathways to the surface, these diamonds are carried upward through narrow channels of rock called kimberlite pipes. They rise fast, lifted from darkness toward light, preserving the conditions of Earth's deep interior like time capsules. Every diamond, no matter how small, was once locked in an environment so intense it could soften steel. Whether shaped patiently over eons or formed in a sudden instant, each crystal records a moment when chaos became order, when something ordinary was transformed into something rare and enduring. Diamonds are not symbols of stillness. They are proof that change, even the most dramatic kind, can happen in silence far below the surface. Mountains, too, are far from motionless. Though they appear ancient and unmoving, many mountain ranges are still rising today. Deep beneath them, massive tectonic plates continue to press together, forcing rock upward year after year. In places like the Himalayas and the Andes, this uplift happens faster than human fingernails grow. The change is too slow for us to see, but it never stops. At the same time, wind, rain, and ice patiently wear mountains down, grain by grain. Erosion and uplift work together in a long balance, one tearing away what the other builds. If time could be sped up, mountains would appear to breathe, swelling upward as continents collide, then slowly softening as gravity pulls them back toward the sea. Some of the stone beneath your feet may once have rested on an ancient ocean floor carried skyward across millions of years. These towering forms remind us that Earth is not frozen in place. It is alive with motion, reshaping itself even as we sleep. Entire continents drift across the planet like immense rafts. Beneath the Earth's thin crust lies the mantle, a vast region of heat and pressure, where solid rock behaves like an incredibly slow-moving fluid. The continents float on this layer rigid slabs, drifting across a hidden sea of stone. They move only a few centimeters each year, barely the width of a fingernail. Yet given enough time, these small movements change everything. Oceans open where continents pull apart. Mountain ranges rise where plates collide. Entire climates shift as land masses wander across the globe. Long ago, all continents were joined together in a single supercontinent called Pangaea, and far in the future, they may come together again in new forms we can barely imagine. Though we feel no motion at all, we are traveling constantly carried across the planet on drifting plates, passengers on a world that never truly rests. Earth endlessly renews its surface through plate tectonics. Nothing on the planet's exterior lasts forever. The ground beneath us is part of a grand cycle of creation and destruction. Where plates crash together, rock folds and thickens, lifting mountains toward the sky. Where they pull apart, molten material rises cooling into fresh ocean crust. Elsewhere, entire plates sink back into the mantle, melting and becoming part of Earth once more. Even the seafloor is temporary. Born at mid-ocean ridges, spreading outward, and eventually swallowed back into the depths, it is constantly replaced on a scale of tens of millions of years. Cliffs, plains, volcanoes, and coastlines all belong to this slow rhythm of renewal. Earth is unique in this way. As far as we know, it is the only planet that recycles itself so completely. Using heat, gravity, and time, it keeps its surface young, dynamic, and alive. The skin of the planet is never still. It is always shedding, rebuilding, and reshaping itself in a quiet, graceful motion that has continued for billions of years. And high above it all, the Himalayas continue to rise. Even now, as clouds drift past their peaks, the slow collision between India and Asia presses upward. Each year, the mountains grow just a little taller, imperceptibly, steadily, patiently. A reminder that Earth's greatest forces do not rush. They work gently, persistently, and without pause. Their rise began roughly 50 million years ago when the Indian plate pressed into the vast Eurasian plate. The crust did not break cleanly. Instead, it buckled and folded, compressing like thick fabric pushed from both sides. That immense collision has never truly stopped. Even now, the plates continue to converge, lifting the mountains upward by just a few millimeters each year. The peaks may look ancient and unchanging, but they are quietly climbing toward the sky while wind, ice, and glaciers sculpt them back down. Every deep earthquake, every subtle tremor beneath the region is a soft echo of that pressure, still working far below the surface. The Himalayas are not monuments of the past. They are the visible result of a collision that began long before humans existed and continues beneath the lives of millions today. In their silent ascent, these mountains remind us that Earth's power does not rush. It applies pressure patiently, relentlessly, shaping continents with the same ease as clay pressed slowly between unseen hands. Continents themselves drift almost imperceptibly. Measured year to year, a continent moves about as fast as human hair grows. The pace feels meaningless, yet over millions of years, this gentle motion redraws the entire map of the world. Continents slide atop the mantle, carried by slow convection currents deep within the planet. The Atlantic Ocean widens a little each year, while the Pacific gradually contracts. Given enough time, familiar coastlines will vanish. Africa will inch closer to Europe. Australia will continue its journey north. And one day, the continents may gather again into a new supercontinent, different from anything Earth has known before. This drifting explains why fossils of the same ancient creatures appear on lands now separated by oceans, and why mountain ranges on distant continents share common origins. The ground feels firm beneath your feet, but it is part of a vast voyage that has never paused since Earth first cooled. The ocean floor tells a different story. Hidden beneath the waves is a surface far younger than most of the continents. While continental rocks can be billions of years old, the seafloor is constantly renewed. Along immense mid-ocean ridges, molten rock rises from below cools and forms fresh crust. This newborn surface slowly spreads outward, drifting away from the ridge. Eventually, it reaches deep ocean trenches where one plate slides beneath another and sinks back into the mantle, erased and recycled. Because of this process, no ocean crust survives longer than about 200 million years, a brief moment in Earth's deep time. The continents endure as ancient survivors floating above this cycle of creation and destruction. If you could watch the planet over millions of years, you would see oceans open and close in slow rhythm, like a long, steady breath. The seafloor is Earth's heartbeat, renewing itself endlessly in darkness and silence. Etched across that seafloor is a remarkable record. Stretching outward from mid-ocean ridges are bands of rock arranged in striking symmetrical patterns like a vast stone barcode. These magnetic stripes mark moments when Earth's magnetic field flipped trading north for south and then back again. As lava emerges and cools, tiny magnetic minerals within it align with the planet's magnetic field. Once solidified, that alignment is locked in place. When the field reverses, newly formed crust records the opposite direction, creating alternating bands that mirror each other across the ridge. By reading these stripes, scientists can trace the history of magnetic reversals stretching back tens of millions of years. This discovery became one of the strongest pieces of evidence for plate tectonics, revealing how the seafloor spreads outward over time. Beneath the oceans lies not disorder, but a precise archive written by magnetism, heat, and the slow pulse of geological time. Even individual rocks can remember Earth's magnetic past. When molten lava cools at the surface, something subtle yet extraordinary occurs. Tiny grains of iron-bearing minerals rotate and align themselves with the planet's magnetic field, acting like countless microscopic compass needles. As the rock hardens, that alignment becomes permanent. Each lava flow preserves a snapshot of Earth's magnetic orientation at the moment it solidified. Scientists study these natural magnets to reconstruct the wandering of magnetic north and the history of polarity reversals. Every flip of the field, every slow drift of the poles is quietly stored in stone. In this way, the planet records its own history without memory or awareness. Fire cools, stone hardens, and the invisible forces shaping Earth are preserved forever in silence. These magnetic signatures became one of the quiet proofs that continents are not fixed and that the seafloor itself is slowly spreading. Locked inside volcanic rock is a silent record of Earth's magnetic rhythm, a coded history of shifting directions and invisible forces shaping the space around our planet. In this way, Earth remembers magnetically its past, written into iron-rich stone, preserved without sound or motion. Every volcano on Earth is linked to a hidden reservoir of molten rock. Far beneath the surface, Each volcano has a deep interior where magma gathers and evolves. These magma chambers are vast pockets of liquid stone quietly feeding eruptions that can reshape landscapes and influence climate far beyond their slopes. Some chambers are small and shallow, others immense and deep, reaching far into the mantle below the crust. Inside these hidden spaces, crystals slowly grow, gases rise, and pressure builds over long spans of time. Eventually, the rock above can no longer contain it. Cracks open, pathways form, and molten material finds its way upward, releasing lava ash and heat onto the surface. Between eruptions, these chambers remain concealed, slowly refilling and changing in silence. Today, scientists can glimpse their outlines using seismic waves, much like medical imaging. For the Earth itself, each volcano is part of a vast internal network, a reminder that beneath quiet plains and sleeping peaks lie glowing worlds of molten stone, breathing slowly in the darkness. Some volcanic eruptions unfold over spans longer than human history. Not all eruptions arrive as sudden explosions. Some are patient and immense, releasing lava steadily for hundreds of thousands of years. When deep mantle plumes deliver extraordinary volumes of magma to the surface, the result can be flood basalts, enormous outpourings of lava that spread across entire regions. These ancient events buried landscapes beneath layer upon layer of rock, forming vast plateaus. The Deccan traps in India and the Siberian traps in Russia stand today as silent remnants of such prolonged fire. During their formation, they released enormous amounts of heat and gas into the atmosphere, altering climate and reshaping the course of life on Earth. Standing on these hardened plains now, it is difficult to imagine rivers of lava stretching to every horizon. Yet these rocks remind us that Earth does not always change through violence alone. Sometimes it transforms through endurance, through the slow, unstoppable advance of fire flowing beneath open skies for ages beyond memory. Basalt forms the dark foundation of the ocean floor. If you could walk across the seabed, nearly every step would rest on basalt, a dense dark rock born from mantle fire. Basalt forms when molten material rises along mid-ocean ridges and cools rapidly upon contact with cold seawater. The result is a continuous crust that spans the ocean basins like a protective shell around the planet. Richer in iron and magnesium than continental rocks, basalt carries its deep color and weight from its origins below. As new basalt forms, older sections slowly drift away from the ridges, eventually sinking back into the mantle at deep trenches where they melt and rejoin the planet's interior. Every portion of the ocean floor participates in this endless cycle of creation and return. Beneath the waves lies a layered archive of cooled magma, quietly recording Earth's most patient motions, one slow renewal after another. Pillow lava forms when fire meets water. When lava erupts beneath the sea, it cools so quickly that its outer surface solidifies almost instantly. Molten rock inside continues to push forward, inflating the hardened shell until it bulges and breaks, forming rounded shapes that resemble stacked cushions or underwater balloons. These formations, known as pillow lava, pile upon one another across the seafloor, marking places where molten rock once flowed silently into the ocean depths. Each pillow preserves a moment when Earth's internal heat met the cold stillness of the sea, freezing motion into stone. Hidden in darkness, these rounded forms are reminders that even beneath miles of water, the planet continues its quiet work. Fire flows, water cools, and the surface of Earth is slowly rebuilt, one gentle eruption at a time. This strange process creates rounded shapes that look like pillows or bubbles stacked gently upon one another. These smooth, bulbous forms, known as pillow lava, can spread across vast stretches of the seafloor. Each pillow is a frozen moment of motion, capturing the instant when molten rock met cold seawater and solidified almost immediately. When geologists discover pillow lava on land, it tells a quiet story that the area was once deep beneath the ocean. There is something eerie and beautiful about these shapes, as if the stone still remembers flowing like liquid before being sealed by the chill of the sea. They are geological sculptures made by time itself, proof that even in the crushing darkness of the deep ocean, Earth's creative forces are always active, shaping the world in silence. Obsidian is volcanic glass formed in an instant. During explosive eruptions, lava can cool so rapidly that crystals never have time to grow. The result is obsidian, a natural glass with a dark reflective surface. It forms when molten rock meets cold air or water and solidifies almost immediately. Smooth and razor-sharp obsidian has been valued by humans for thousands of years, shaped into blades, tools, and ornaments. Yet behind its mirror-like surface lies a story of sudden transformation. Flowing fire stopped mid-motion. Intense heat turned into fragile stone. Obsidian breaks easily, but when it fractures, it forms elegant curved patterns called conchoidal fractures, as though the rock still remembers the direction in which it once flowed. This glassy stone stands as one of geology's most striking contrasts, born in violence, yet perfectly still fragile, yet timeless, a piece of fire preserved forever in solid form. Some rocks quietly preserve bubbles of Earth's ancient atmosphere. Trapped within microscopic cavities, scientists have discovered tiny pockets of air that have survived for millions of years. These bubbles act as natural time capsules, sealing the chemical signature of long vanished skies. By studying them, researchers can learn how much oxygen once filled the air, how much carbon dioxide warmed the planet, and how volcanic activity or early life altered Earth's atmosphere. Some of these bubbles formed in cooling lava, others in sediments or ice. Each one contains a trace of an ancient breath, a whisper of the air that surrounded early forests, giant reptiles, or the first organisms to breathe. Holding such a rock is like holding a fragment of a vanished sky, a delicate record of the ever-changing atmosphere that connects all life across deep time. There are mountains hidden beneath the sea that rise higher than Everest. Far below the ocean's surface, vast mountain ranges stretch across the planet unseen and unlit. Along the mid-ocean ridges, enormous chains of volcanic mountains extend for tens of thousands of miles. Measured from their base to their summit, Many of these underwater mountains rise higher than Everest does above sea level. They remain hidden in darkness, buried under immense pressure, yet they are among the most active regions on Earth. Lava continually emerges from cracks in the crust, slowly building new peaks and valleys. Some giants, like Mauna Kea, when measured from the ocean floor, surpass even the highest Himalayan summits. These submerged ranges remind us that much of Earth's grandeur exists beyond human sight, vast kingdoms of rock growing and shifting quietly beneath the waves. Earth's deepest point lies almost as far below sea level as airplanes fly above it. In the western Pacific Ocean, the Mariana Trench plunges so deep that if Mount Everest were placed inside its peak, would still be buried beneath more than a mile of water. The trench's deepest known point, Challenger Deep, reaches nearly 7 miles below the ocean's surface, a distance comparable to the cruising altitude of commercial aircraft. Down there, pressure is so intense it could crush steel, yet life still finds a way to survive. Strange organisms inhabit the darkness, thriving among mineral-rich sediments. The trench marks a subduction zone where one tectonic plate slides beneath another and sinks back into the mantle. It is not only the lowest place on Earth, but also one of the planet's great engines of renewal, quietly recycling the crust and reminding us how small the visible world is compared to the vast depths below. Even when the ground feels completely still, the planet is never truly at rest. Earth hums with countless micro-earthquakes that pass unnoticed each day. Across the globe, thousands of tiny tremors ripple through the crust, releasing small bursts of energy as the planet adjusts to stresses deep below. These movements are too gentle for humans to feel, yet they reveal a world constantly balancing itself. The ground beneath you is always shifting, stretching, and settling in slow, patient rhythms. Earth is not a silent stone, but a living system softly murmuring as it reshapes itself moment by moment, even as you rest. Scientists use incredibly sensitive instruments to record these whispers, turning faint vibrations into detailed maps of shifting faults and hidden magma flows. Together, these signals blend into a background hum that never truly fades. It is the quiet pulse of a living planet. This constant trembling tells geologists where faults are slowly creeping, where pressure is silently building, and where volcanic systems are beginning to stir. The stillness we experience on the surface is an illusion. Beneath every mountain, forest, and sea, Earth is moving in countless subtle ways, sighing, cracking, and settling in slow, secret rhythms that carry the story of the planet's restless heart. Earthquakes can even make entire rivers run backward. When the ground shakes with enough force, the shape of the land itself can change in an instant. During powerful earthquakes, sections of the crust may tilt or shift so suddenly that rivers are briefly forced to reverse their flow. This rare event was recorded during the Great New Madrid earthquakes in the early 19th century, when parts of the Mississippi River temporarily flowed upstream. Sudden movements along faults can lift one side of the land or drop another, creating natural dams or reshaping valleys. For a brief moment, Earth's internal forces can overpower gravity itself, redirecting water that has flowed the same way for thousands of years. When balance returns, rivers carve new paths through the altered terrain, leaving behind a landscape forever changed. These events reveal the immense strength of geological motion, showing that even something as ancient and reliable as a river can be turned back by forces deep within the planet. Some faults move without drama or sound at all. Not all tectonic motion announces itself with shaking or destruction. Along certain fault zones, the crust slides so slowly and smoothly that no earthquake is felt at the surface. This phenomenon, known as fault creep, releases stress in tiny continuous increments. The motion is invisible to the human eye, but precise instruments can detect movements of only a few millimeters per year. In places like California and Turkey, some faults glide quietly, while neighboring sections remain locked and tense. These creeping areas may reduce the likelihood of large earthquakes locally, but they can also transfer stress to other regions. This delicate balance between tension and release is part of Earth's constant adjustment. Even in silence, the ground beneath us is always shifting, whispering through time, as the planet reshapes itself grain by grain. At the very center of Earth, temperatures soar higher than the surface of the sun. Deep within the planet lies a core made of solid and liquid metal under pressures almost impossible to imagine. Temperatures there rise above 9,000 degrees Fahrenheit, rivaling and even exceeding the visible surface of the sun. This heat is a remnant of Earth's violent birth, combined with the steady release of energy from radioactive decay deep inside. Though no human will ever see the core directly, its influence reaches everywhere. It powers volcanic eruptions, drives plate tectonics, and generates the magnetic field that shields life from harmful cosmic radiation. The outer core flows like a vast ocean of molten iron, while the solid and inner core rotates slightly faster than the layers above it. This hidden furnace acts like a planetary engine, quietly sustaining Earth's warmth movement and long-term stability. There may even be an entire ocean hidden deep within the mantle. Far below the crust, where rock glows with heat and pressure, scientists have discovered minerals capable of storing enormous amounts of water within their crystal structures. These findings suggest that a volume of water comparable to all the oceans on Earth may exist hundreds of miles below the surface, locked inside solid rock rather than flowing freely. This hidden reservoir is not an ocean as we know it, but a vast store of the same substance that makes life possible. Tectonic plates may carry water downward into the mantle where it is held for millions of years before returning to the surface through volcanic eruptions and rising plumes of magma. This deep water cycle may help explain why Earth has maintained oceans for so long. Even in the hottest stone water finds a way to persist, waiting patiently inside the planet for ages beyond human memory. In rare places, crystals can grow larger than a person in total darkness. Deep beneath the deserts of northern Mexico lies one of the most extraordinary geological chambers ever discovered. Inside the Cave of the Crystals, enormous gypsum formations stretch more than 30 feet in length. Each crystal grew slowly over hundreds of thousands of years in perfect stillness, nourished by warm, mineral-rich water that once filled the cave. When that water eventually drained away, The crystals were left behind, towering and translucent, gleaming softly like frozen moonlight in the humid air. Their immense size is a testament to patience rather than force, showing what can form when conditions remain stable for unimaginable lengths of time. These underground cathedrals remind us that Earth creates not only through violence and upheaval, but also through long periods of quiet, uninterrupted growth hidden far from the surface. Entering the cave feels like stepping beyond the ordinary world, not into a place shaped by violence or fire, but into a chamber sculpted by patience and balance. Here, perfection is not rushed. It unfolds slowly, molecule by molecule, in silence. The conditions required to form such immense crystals are almost impossibly rare, a precise harmony of heat, pressure, water, and time. These towering formations remind us that even the hardest materials on Earth can bend, grow, and transform when given enough patience. They are geology's most graceful expression of stillness, beauty created not by force, but by time itself. Deep beneath the surface of Mexico lies one of the most astonishing geological wonders ever discovered. The Cave of the Crystals, found by miners in the year 2000, contains gigantic gypsum formations that shimmer like beams of frozen light. Some crystals stretch across the chamber, weighing tens of tons, their translucent faces catching and scattering every faint glimmer. They grew in mineral rich groundwater that remained at a stable temperature for hundreds of thousands of years, allowing atoms to arrange themselves with extraordinary precision. When the water was finally drained, the crystals stopped growing, preserving a moment of deep geological time. The cave's heat and humidity are so intense that humans can only enter briefly wrapped in protective suits. Yet for those short moments, explorers stand inside a cathedral built by chemistry and silence, a place shaped not by hands, but by Earth's slow and careful touch. In other parts of the world, entire landscapes are quietly reshaped by salt moving like a frozen tide. Beneath thick layers of rock, ancient deposits of salt left behind by long vanished seas begin to rise. Though solid to the touch, salt behaves like a slow flowing fluid under immense pressure. Over millions of years, it pushes upward, bending and fracturing the rock above it, forming massive structures known as salt domes. Some of these domes stretch for miles underground, invisible from the surface, yet powerful enough to trap oil and gas, shaping human history and industry. From above, the land appears calm and unmoving. Below, salt climbs steadily upward, proof that even stone can flow when time stretches long enough. Each dome carries the memory of ancient oceans that evaporated, leaving behind minerals that still rise toward the sky in silence. What appears to be wood turned to stone is in truth a masterpiece of atomic replacement. Petrified wood begins as a fallen tree buried beneath layers of ash or sediment where oxygen is scarce. Mineral-rich groundwater slowly seeps through its cells, and over thousands to millions of years, each organic structure is replaced atom by atom with quartz. Every ring fiber and knot is preserved with astonishing detail. The result still looks like wood, but feels cold, heavy, and timeless in your hands. Trace elements sometimes color the stone in deep reds, golds, or greens, painting natural artwork through its grain. Holding petrified wood is like holding memory made solid. A once living tree transformed into crystal, reminding us that nothing in nature truly disappears. It simply changes form, carrying its story forward in stone. Coal, too, began as life reaching toward the sun. Long before humans existed, vast forests thrived in warm, swampy worlds. When these ancient trees and plants died, they fell into waterlogged environments where decay slowed almost to a stop. Layer by layer, organic material built up buried under its own weight. Over millions of years, heat and pressure transformed this compressed plant matter into coal, a rock rich in carbon. Inside every piece lies sunlight, captured by prehistoric leaves under skies long gone. When coal burns, it releases that ancient energy once again, a faint echo of sunlight stored for eons. It is a reminder that Earth remembers everything, preserving the past, not only in stone, but in energy waiting patiently to be released. The process that created coal is a quiet story of transformation, of life slowly becoming stone, of sunlight once captured by leaves beneath ancient skies, compressed into dark seams beneath our feet. Every piece of coal carries the memory of vanished forests, the breath of a world that no longer exists. What looks like an ordinary black rock is in truth a fossilized echo of green canopies, humid air, and prehistoric rain. A reminder that Earth stores its past not only in fossils, but in energy itself. Oil, too, began as life floating beneath ancient waves. Long before dinosaurs walked the land, Earth's oceans teemed with microscopic plankton. These tiny organisms absorbed sunlight and carbon, forming the foundation of marine food webs. When they died, their remains drifted down and settled into soft layers of mud on the seafloor. Buried deeper with time, heat, and pressure, transformed their carbon rich bodies into liquid hydrocarbons. Trapped within porous rock, these ancient molecules waited for millions of years. Every drop of oil once moved gently through a primordial sea, carrying the energy of sunlight, captured by the simplest forms of life. In this way, modern civilization is powered by the deep biological memory of the planet chemistry and time woven together in darkness far below the surface. Every grain of sand tells the story of a mountain that no longer stands. Before it rested on a shoreline or desert floor, each grain was once part of something vast. A cliff, a peak, a plateau lifted high by tectonic forces. Wind, water, ice, and gravity worked patiently, breaking that rock down fragment by fragment. Rivers carried it away. Glaciers dragged it across continents. Waves rolled it endlessly until sharp edges softened into smooth crystals. Under a microscope, a single grain reveals its origin: quartz from ancient continental crust, volcanic glass from long cooled eruptions, coral fragments from vanished reefs. A handful of sand is the library of Earth's past, countless landscapes, reduced to glittering dust, waiting to be pressed together again and reborn as stone. In some deserts, the sand itself can sing. When dunes shift in rare places, Around the world, a deep resonant sound rises from the moving slopes. These singing dunes, found in regions like the Sahara, the Arabian Peninsula, and parts of South America, produce tones so steady they resemble a musical note held in the air. The sound emerges when thousands of grains slide together in perfect synchrony, vibrating at a shared frequency. For this to happen, the sand must be remarkably uniform and perfectly dry. The result is haunting, a low hum that seems to come from the land itself. Ancient travelers believed these sounds were voices of spirits hidden beneath the dunes. In reality, it is physics given rhythm, friction motion, and gravity turning the earth into an instrument that plays its own slow ancient song. Some beaches are built almost entirely from shells. In certain parts of the world, the sand beneath your feet is not ground rock at all, but the remains of countless marine lives. Tiny fragments of coral mollusk shells and microscopic organisms accumulate over time, broken down by waves into pale, soft grains. These beaches glow in shades of white pink or cream, reflecting sunlight with a gentle warmth. Each step presses against the history of oceans, built not by mountains crumbling, but by life itself repeating its quiet cycle. Birth, growth, death, and return. Even here, the land is shaped by living things, reminding us that geology and biology are never truly separate. They are partners in the long story of Earth. Along certain coastlines, the sand beneath your feet was not carved from stone, but patiently assembled by life itself. Over countless generations, the shells of tiny marine organisms, mollusks, corals, and microscopic foraminifera broke apart under waves and tides, reduced to grains so fine they resemble pale dust. These biological sands reflect light differently than rock-borne beaches. They glow white under tropical sun, blush softly pink where coral fragments mix in or shimmer faintly gold when algae once rich in calcium leave their trace. Each grain once belonged to a living body drifting through warm seas. Walking along such shores is like moving across the remains of invisible cities where life built its architecture slowly, only to be gently dismantled and returned to the land by water and time. The famous white beaches of places like the Bahamas and the Maldives are not accidents of geology, but living records of biology shaping beauty grain by grain. Not all beaches wear pale colors. Across the planet, shorelines appear in black, green, pink, and even deep red. These colors are geological signatures written in sand. Black beaches often form where volcanic lava met cold seawater, shattered instantly into dark glass fragments. Green sands emerge where crystals of olivine, born deep in the mantle, are carried to the surface and sorted by waves. Pink beaches owe their hue to crushed coral and shells blended into lighter grains, while red sands gain their color from iron-rich rocks weathered and oxidized over time. Each shoreline tells a different story about fire-water chemistry and erosion. With every wave, these grains are rearranged again and again, blending Earth's elements into shifting patterns of natural art. The planet is constantly repainting itself, one tide at a time. Glaciers carve landscapes not with speed, but with relentless patience. Though they appear frozen, and still glaciers flow like rivers made of stone cold time. Snow accumulates, compresses, and transforms into dense ice, heavy enough to creep downhill under its own weight. As these frozen rivers move, they grind against bedrock, scraping valleys wider and deeper, polishing stone smooth and dragging enormous boulders for miles. When glaciers retreat, they leave behind unmistakable signatures: broad U-shaped valleys, scattered erratic rocks far from their origin, and long narrow lakes filling the paths they once occupied. From the carved fjords of Norway to the smooth granite domes of Yosemite glaciers have shaped landscapes across nearly every continent. Even now, they continue their quiet work, reducing mountains to fine mineral dust that drifts across oceans. They are architects of terrain, sculptors, guided by temperature and gravity, reshaping the planet without sound. Some glaciers move fast enough for their motion to be seen within hours. While most advance only inches per day, a few surge dramatically when conditions align. Meltwater seeps beneath the ice, reducing friction between glacier and ground, allowing massive slabs of ice to slide forward with startling speed. In parts of Greenland and Alaska, scientists have watched glaciers shift visibly, their surfaces cracking and folding as they accelerate. From afar, the movement feels unreal, solid ice behaving like a flowing liquid. Yet the force carried by these surges is immense, capable of reshaping valleys and transporting rock weighing thousands of tons. To witness a glacier in motion is to see geological time briefly speed up, revealing that even the coldest forces on Earth are alive with energy and change. Deep within a glacier, ice behaves less like stone and more like a slow-moving fluid. Under intense pressure and temperatures just below freezing ice, crystals begin to deform. They stretch, bend, and slide past one another, allowing entire ice masses to creep downhill continuously. This internal flow resembles thick honey poured in extreme slow motion. Layer upon layer folds inward, recording stress and movement like rings in a tree. What seems rigid from the surface is inside crystally yielding. This strange behavior allows glaciers to persist, to move, to sculpt, and to endure. It reminds us that on Earth, solidity is often an illusion. Given enough time and pressure, even ice learns how to flow. This slow motion flow gives glaciers their quiet elegance, their ability to reshape entire mountain ranges without haste. Given enough time and pressure, even materials we consider rigid can behave like fluids. Laboratory experiments show ice crystals bending, sliding, and reorganizing under weight, revealing how matter itself softens when patience is long enough. What seems fixed becomes flexible. What appears permanent learns how to move. Earth's most dramatic changes rarely arrive in a single violent moment. They unfold through persistence, through pressure applied gently, endlessly, until the planet yields. Sometimes geology preserves moments so brief they feel impossible to keep. On slabs of ancient sedimentary rock, scientists have discovered tiny circular impressions made by raindrops that fell hundreds of millions of years ago. Each mark is the frozen echo of a storm that passed over a world long vanished. Soft mud received the drops, and almost immediately new sediment buried them, sealing their shapes in darkness. Over time, the layers hardened into stone. When exposed again, they reveal weather from deep time. A rainstorm that lasted minutes, now recorded for eternity. These fossilized raindrops remind us that even the most fleeting events can endure when chance and geology align. A single stone can still carry the rhythm of ancient rain. For a long time, fossils were thought to preserve only the hardest parts of life: bone, shell, teeth, but the earth sometimes keeps far more delicate memories. Under rare conditions, soft tissues can survive. In exceptional fossils, scientists have found impressions of skin muscle and feathers. Some even preserve traces of pigment, allowing researchers to reconstruct the colors of dinosaurs and ancient birds. Mineral rich water seeped into the remains before decay could erase them, replacing organic material molecule by molecule with stone. What remains is not just shape, but texture pattern and hint of motion. These fossils collapse time. They allow us to sense warmth, color, and movement from creatures that walked beneath suns long gone. Stone does not merely remember structure, sometimes it remembers life itself. Long before animals moved or plants reached upward, life began in silence. In shallow, ancient seas, simple microbial communities built layered structures by trapping sediment and growing slowly toward light. These formations, known as stromatolites, are among the oldest records of life on Earth. Some are more than 3.5 billion years old. They form not through speed or complexity, but through repetition and patience, layer upon layer, life altering stone. Remarkably, stromatolites still grow today in a few isolated places, continuing a process nearly unchanged since the planet's youth. To look at one is to look into Earth's biological beginning, when life first learned how to shape the world gently, persistently, without intention or haste. There was a time when Earth nearly disappeared beneath ice. Around 700 million years ago, the planet entered a phase known as snowball Earth. Ice sheets spread from the poles to the equator, locking oceans beneath thick frozen shells and reflecting sunlight back into space. For millions of years, Earth became a pale, silent sphere. Yet life did not vanish. It endured in hidden refuges, beneath ice near volcanic warmth, within pockets of liquid water. Deep below the frozen surface, biology waited. Volcanoes never stopped during this frozen age. They continued releasing carbon dioxide into the atmosphere, gas that could no longer be absorbed by oceans sealed under ice. Slowly, heat began to accumulate. The planet warmed, ice retreated, oceans thawed. When the melt finally came, it reshaped Earth, rapidly flooding continents and altering chemistry across the globe. This return of warmth may have opened the door for complex life to flourish. Snowball Earth was not an ending, it was a reset, a planetary breath held and released. Geology teaches us this lesson again and again. Earth changes not only through catastrophe, but through endurance, through quiet accumulation, through materials yielding slowly to pressure, time, and energy. Ice flows, stone bends, life persists, and the planet remembers everything, recording its story in layers, patterns, and scars that whisper long after the forces that shaped them have faded. With the oceans locked beneath thick ice, volcanic gases had nowhere to go. Normally, carbon dioxide would dissolve into seawater, but during this frozen age, the surface was sealed. Slowly, the gas accumulated in the atmosphere, building an invisible blanket that trapped heat. For millions of years, this process continued in silence. Then, once melting began, it did not stop gently. As ice retreated, darker rock and water were exposed, absorbing more sunlight and accelerating the warming. In a relatively short geological moment, the planet shifted from a white frozen sphere back to blue-green oceans and flowing seas. Torrents of meltwater reshaped the land, erosion intensified, and new chemical pathways may have opened that favored early life. In this sense, volcanoes acted as Earth's quiet guardians. Erupting patiently beneath ice, they preserved the possibility of warmth. An age of deep cold ended not in collapse, but in renewal. Even at its most frozen, the planet was never truly dormant. Fire waited below. The air you breathe began as a waste product. Billions of years ago, tiny microbial communities lived in shallow seas long before plants or animals existed. These early organisms, ancestors of modern cyanobacteria, learned to harness sunlight in a powerful new way. By splitting water molecules during photosynthesis, they released oxygen into their surroundings. At first, this oxygen did not accumulate in the air. Instead, it reacted immediately with iron dissolved in the oceans, forming heavy rust-like minerals that sank to the sea floor. Only after vast amounts of iron were consumed did oxygen begin to spill into the atmosphere itself. This slow transformation, known as the Great Oxidation Event, reshaped the planet. It altered the chemistry of oceans, skies, and rocks, and opened the door for complex cells to evolve. Every breath taken today traces back to those simple microbes quietly changing the world molecule by molecule. Across ancient landscapes, that transformation is written in stone. In many parts of the world, layered bands of red and gray rock lie exposed at the surface. These banded iron formations are geological records of the moment Earth began to breathe. Each layer formed as oxygen released by microbes combined with iron in seawater, settling into sediments over immense spans of time. As these layers accumulated, they hardened into rock, preserving the rise of oxygen in physical form. Today, these formations supply much of the iron used in modern civilization. Steel cities and machines owe their existence to reactions that began in ancient seas. Each stripe is a chapter in the planet's awakening, marking the transition from a lifeless atmosphere to one capable of supporting forests, animals, and eventually human life. Before that change, the oceans themselves may have looked unfamiliar. Long before blue skies and oxygen-rich air, Earth's seas were likely tinted with deep reds and purples. Ancient microbes dominated these waters, using sulfur compounds instead of oxygen to power their metabolism. Their pigments absorbed sunlight differently, coloring the oceans in hues that feel almost alien today. Under a hazy orange sky, these sulfur-based ecosystems thrived in chemical-rich environments. As oxygen-producing organisms, spread, the chemistry of the oceans shifted. The purple tones faded, replaced by the clear blues we recognize now. This was not a simple color change, but a complete reordering of planetary chemistry. A sulfur world gave way to an oxygen world. For a brief window in deep time, Earth glowed in colors that no human eye would ever see again, a reminder that the planet we know is only one version among many it has already been. Violet seas beneath a muted sun were once the backdrop of life on Earth, a time when biology was still experimenting with light itself long before forests spread across land, before coral reefs formed in warm oceans, before any creature drew breath from the air. These early worlds remind us that the planet has worn many faces, most of them now completely erased. Entire mountain ranges have come and gone without leaving a visible trace. The continents we recognize today are only the latest surface arrangement in a long sequence of transformations. Across deep time, mountains have risen to immense heights only to be slowly dismantled by wind, water, ice, and gravity. Grain by grain, even the tallest peaks are worn down. What sometimes remains are their deep roots, hardened crystalline rocks buried far beneath younger layers, waiting quietly to be discovered. Some of the oldest continental cores once supported vast ranges that no longer exist, flattened into plains so ancient their origins are nearly impossible to imagine. Over hundreds of millions of years, erosion can erase a mountain as thoroughly as waves smooth a stone on a shore. The planet never stops rebuilding itself. What feels permanent to us is only a temporary sculpture in geology's endless work. Every plain was once a summit, and every rock still carries the memory of a mountain that no longer stands. The continents themselves have not stayed together. Again and again they have collided, merged, and torn apart. Driven by heat rising slowly from Earth's interior, the crust fractures and shifts, rearranging the surface like pieces of a puzzle in motion. When continents collide, rock is folded and buried, transformed by immense pressure and heat. When they pull apart, new oceans open and fresh crust is born. This repeating pattern, known as the supercontinent cycle, has unfolded multiple times across Earth's history. Its evidence is written across the planet in matching fossils, rock layers, and mountain belts found on shores now separated by vast oceans. The land beneath us is not fixed. It is a traveler carrying fragments of many ancient worlds within its foundations. Before the world we know, there were other giants. Long before Pangea, and even before Rodinia Earth assembled and broke apart several massive supercontinents. At least 6 are thought to have existed, each spanning much of the globe, each with its own mountains, seas, climates, and rhythms. Names like Nuna, Columbia, Rodinia, Gondwana, and others mark these vanished configurations. When they formed, life was often simple and microscopic, yet their presence reshaped ocean circulation, atmospheric chemistry, and climate itself. Each breakup altered evolutionary paths, isolating species, changing environments, and setting the stage for what would come next. The continents we inhabit today are remnants of these earlier giant survivors of a cycle that stretches back billions of years. Studying them is like reading Earth's autobiography, written in drifting stone, where even continents are temporary and nothing remains whole forever. Pangaea was only the most recent of these great gatherings. Around 250 million years ago, nearly all of Earth's land merged into a single immense supercontinent surrounded by a vast global ocean. This enormous landmass stretched from pole to pole, linking regions that are now oceans apart. Its interior grew dry and extreme, far from the moderating influence of the sea, while its coastlines supported early forests and reptiles. Over time, internal stresses and rising heat began to pull Pangaea apart. Cracks widened, magma rose, and new oceans slowly opened. From that breakup emerged the continents we recognize today, still drifting, still changing, still part of the same ancient cycle. Over tens of millions of years, heat rising from deep within the planet slowly built enormous pressure beneath the crust. Eventually, the surface could no longer hold together. Fractures formed, land began to split. Through these widening seams, new oceans were born. The Atlantic opened, and the continents started their long, silent journey toward the positions we recognize today. On the opposite shores of that ocean, fossils of the same plants and animals still appear quite proof that these lands were once joined. The breakup of Pangaea reshaped coastlines, redirected winds and currents, and altered climates across the globe. It set the foundation for the modern world, guiding the evolution of life and the geography we inhabit. Yet Pangaea was never unique. It was neither the first great gathering of continents nor the last. It was simply one moment in Earth's endless cycle of separation and reunion. Far beneath the Pacific Ocean today, the earliest movements of the next supercontinent may already be unfolding. The tectonic plates continue their slow migration, driven by heat and motion deep within the mantle. Many scientists believe that in 2 to 300 million years, the continents will once again assemble into a single vast landmass. Some models suggest the Pacific will gradually close as Asia and the Americas move together, forming a future continent, sometimes called Amasia. Other scenarios envision the Atlantic shrinking, instead pulling Europe and the Americas back toward one another. The exact outcome remains uncertain, but the process itself is unavoidable. The same unseen forces that tore Pangaea apart are still at work, shifting the surface of the planet millimeter by millimeter. Our maps feel permanent, but they are only temporary sketches of a world in motion. Australia offers one of the clearest examples of this quiet migration. Beneath the continent, its tectonic plate is steadily drifting northward at a rate of just a few centimeters each year. Over vast spans of time, that gentle pace becomes monumental. In millions of years, Australia will collide with Southeast Asia, lifting new mountain ranges and reshaping entire coastlines. Satellites already measure this movement with remarkable accuracy, confirming that the continent is on a slow but unstoppable voyage. This motion is powered by convection currents deep in the mantle, where heat from Earth's interior moves massive slabs of crust like rafts on a slow, molten sea. As Australia travels, climates shift, ecosystems adapt, coral reefs grow where land once stood, and deserts gradually migrate. One day, new mountains will rise, where ocean now separates two worlds. Africa, too, is in the early stages of transformation. Across eastern Africa, a vast rift stretches for thousands of kilometers, marking a place where the continent is slowly pulling itself apart. Earthquakes, volcanoes, and thinning crust all reveal that this region is weakening. In tens of millions of years, a new ocean may flood in separating a large portion of eastern Africa from the rest of the continent. Lakes like Tanganyika and Malawi already fill the deep scars of this rift, offering a glimpse of what may come. Standing along its edges today is like witnessing the first breath of a future continent. The change is almost impossibly slow, yet it is happening now, quietly shaping the geography of a distant world. Iceland provides a rare window into this process at the surface. The island sits directly atop the mid-Atlantic ridge, where two tectonic plates are moving apart. Here, molten rock rises through a long tear in the crust, cooling to form new land. Iceland is a meeting place of fire and ice, where glaciers rest beside active volcanoes and geothermal heat warms the ground. Geysers, lava fields, and hot springs all reveal the restless energy below. With each eruption, the island grows and reshapes itself, reminding those who live there that their land is still being built. Iceland is not a finished landscape, but a moment caught in the act of creation, a living example of the forces that continuously remake the earth. This rare position makes Iceland one of the only places on Earth where a major plate boundary rises above the ocean, exposed to open air. Here, scientists can observe the raw mechanics of plate tectonics, directly watching continents pull apart in real time. Iceland is not just land, it is a living experiment, a place where the planet is actively creating itself, poised between the icy waters of the North Atlantic and the glowing heat of Earth's interior. Fire and ice coexist here, revealing the balance that shapes our world. Far out in the Pacific, a very different process builds the Hawaiian Islands. Deep beneath the ocean floor, a column of heat rises from the mantle, forming what geologists call a hotspot. Unlike tectonic plates, this hotspot remains nearly stationary as the Pacific plate slowly drifts northwest. Molten rock punches through the crust again and again, forming a chain of volcanoes. Each new island emerges above the hotspot, while older ones are carried away, slowly eroded by wind and waves. Over millions of years, this has created a sweeping trail of islands and submerged mountains stretching thousands of kilometers across the ocean floor. The youngest island, Hawaii itself, still glows with flowing lava, while older islands farther northwest have worn down into low coral atolls. By following this chain, scientists can reconstruct the movement of the Pacific plate across deep time. The hotspot remains fixed, while the surface of the planet glides silently overhead. Each island marks a moment in Earth's motion, a record of time written in cooling stone. In North America, another immense system lies hidden beneath a calm landscape. Below the forests, lakes, and geysers of Yellowstone rests one of the largest volcanic systems on the planet. Beneath the surface, vast magma reservoirs stretch for tens of kilometers, feeding the region's steaming vents and erupting geysers. The boiling pools and sudden fountains of water are gentle surface expressions of an enormous heat source below. Although Yellowstone is not expected to erupt catastrophically anytime soon, its past eruptions reshaped much of the continent, spreading ash across enormous distances. Today, scientists closely monitor subtle ground movements and seismic signals, watching the slow breathing of the system. Yellowstone stands as both a place of natural beauty and a reminder that even the most peaceful landscapes can sit atop ancient, restless forces. When volcanoes of ordinary size erupt, their effects are usually regional and temporary. But when a supervolcano erupts, the consequences can be global. These rare events eject immense volumes of ash and sulfur rich gases into the atmosphere, dimming sunlight and cooling the planet for decades or even centuries. Evidence of such eruptions appears in ice cores, ash layers, and climate records linked to sites like Yellowstone and Toba. In their aftermath, volcanic winters can strain ecosystems, alter rainfall patterns, and reshape the course of evolution. Though incredibly rare, these eruptions reveal the delicate balance between Earth's interior and the thin layer of life on its surface. Even so, supervolcanoes are part of the planet's long cycle, moving material between the crust and the atmosphere and clearing paths for renewal. Fire and life have always been intertwined in Earth's history. The largest known volcanic eruption in recent geological time occurred around 74,000 years ago in what is now Indonesia. At Lake Toba, a colossal explosion released more than 2,000 cubic kilometers of ash and magma, leaving behind a vast caldera still visible today. Ash spread across continents, skies darkened, and global temperatures likely dropped for years. Some researchers suggest this event placed immense pressure on early human populations, though life endured. What remains is a quiet reminder of the power stored beneath the surface. A single eruption brief, in geological terms, capable of influencing climate landscapes and living species across the planet. And yet, even after such immense disruption, Earth continued forward, cooling, stabilizing, and allowing life to adapt once more. Beneath all these stories runs a gentle truth. The planet is never truly still. Heat rises, stone flows, continents wander, creation and destruction move together slowly and patiently across unimaginable spans of time. And now, as these ancient forces continue their quiet work far below, you can allow your own thoughts to slow. The earth carries its restless energy beneath you, steady and enduring. You are safe on its surface, held by a world that has learned over billions of years how to change without breaking. Let the motion beneath the ground fade into the background. Let your breathing soften, and as the planet continues its slow, silent creation, you can rest, gently drifting toward sleep. Long after an eruption has ended, the planet continues to speak through the air itself. Volcanic gases can linger high in the atmosphere for years, subtly cooling the earth and painting sunsets in deep shades of red and violet. These vast eruptions are so powerful that they eclipse anything witnessed in recorded history. Today, the quiet lake filling an ancient caldera appears calm and reflective. Yet beneath its still surface lies one of Earth's deepest scars, a reminder that the planet's greatest acts of creation are often shaped through destruction. Some eruptions scatter ash so fine that it can circle the globe many times. High above, weather systems' microscopic volcanic particles drift silently, carried by powerful winds that wrap around the planet. Ash from eruptions such as Mount Pinatubo or Krakatoa has been detected long after the explosions faded, preserved in ice cores and ocean sediments. These tiny fragments scatter sunlight, softening temperatures and igniting vivid sunsets that once inspired painters and poets alike. Even centuries later, traces of these eruptions return to Earth, settling quietly into snow and sediment. No eruption exists in isolation. Every plume, no matter how distant, becomes part of the shared atmosphere that surrounds us all. The air you breathe today carries faint echoes of Earth's ancient fires, subtle reminders that the calmest sky still holds memories of molten breath rising from below. In a few rare places on Earth, lava never fully cools. Within certain volcanic craters, molten rock remains exposed for decades, sustained by a delicate balance of heat and rising magma. Lava lakes, such as those found at Erta Ale in Ethiopia or Kilauea in Hawaii, churn slowly like glowing seas. Their surfaces crust over, then break apart again, revealing incandescent orange light beneath the darkness of night. These lakes persist because fresh magma continually circulates upward, keeping the molten surface alive. To observe one is hypnotic, a living furnace breathing in slow, steady rhythms. These fiery pools offer scientists rare glimpses into the behavior of magma insights that cannot be recreated in laboratories. Each lava lake is a quiet declaration that Earth's inner fire has never gone out, resting just beneath a thin, cooling shell. Sometimes eruptions give birth to storms of light. Within towering ash, clouds' particles collide and rub together, building enormous electrical charges. When this energy discharges, lightning flashes through the plume, illuminating the sky with branching bolts of white and violet. Volcanic lightning is born not from rain and clouds, but from rock gas and friction alone. For brief moments, ash columns glow like thunderous towers of fire. Scientists study these flashes closely, as the intensity of lightning can reveal how violently material is being ejected. To witness such a storm is to see Earth's elements unite solid liquid gas and electricity into a fleeting display of raw power and unexpected beauty. In colder regions, volcanoes meet ice in dramatic fashion. When magma rises beneath glaciers, immense volumes of ice melt almost instantly. The resulting steam expands violently, triggering explosive eruptions beneath the frozen surface. These events can tear through ice caps, releasing floods and ash that surge down valleys. Iceland, resting atop both ice and fire, is especially shaped by these hidden eruptions. The landscapes left behind are unlike any other flat-topped mountains and ridges formed where lava cooled beneath thick ice. These structures, known as tuyas, stand as monuments to the union of heat and cold. Each eruption beneath a glacier reshapes the land, showing that even opposing forces are bound together in Earth's endless cycle of transformation, and sometimes creation happens before our very eyes. Within human memory, entire islands have risen from the sea, pushed upward by volcanic force. Where waves once rolled, uninterrupted black rock breaks the surface, steaming and glowing as it meets the open air. Over time, these newborn islands cool, erode, and welcome life, becoming part of the planet's ever-changing face. Earth is never finished. Beneath the quiet oceans and calm skies, it continues to build release and renew itself slowly, patiently, endlessly. And as these ancient processes unfold far below, you can let your thoughts drift gently away. The planet holds its fire beneath you, steady and enduring. You are safe upon its surface, and as earth breathes in its deep rhythms, you may rest, softly floating towards sleep. Beneath the ocean's surface, some volcanoes erupt with such strength that they slowly build islands from the seafloor upward. In recent history, eruptions near Iceland, Japan, and Tonga have pushed fresh land into the light, where new rock steamed and cracked beneath the open sky. Some of these fragile islands were quickly worn away by waves and storms, while others endured cooling and hardening enough to become permanent parts of the map. These newborn islands offer a rare glimpse into Earth's creative process as it happens. They reveal the same forces that once raised continents from the sea long before human memory. Over time, birds arrive, seeds take root, and life follows, transforming raw lava into living ecosystems. Each rising island reminds us that the planet is still at work, endlessly reshaping its surface. Earth continues to build, erase, and begin again, one eruption at a time. Some lakes, however, hide a quieter and more dangerous energy. In parts of Africa, deep volcanic lakes hold vast quantities of dissolved carbon dioxide trapped beneath their surfaces. For years, even centuries, the gas remains locked in the water like bubbles in a sealed bottle. But if temperature or pressure shifts suddenly, the gas can escape all at once, rising in a silent, invisible cloud. In the 1980s, Lake Nyos in Cameroon released such a burst, suffocating life in nearby valleys without warning. Today, scientists carefully monitor these lakes, installing systems that slowly vent the gas to prevent future disasters. This rare phenomenon, known as a limnic eruption, is a powerful reminder that even the calmest waters can conceal immense force. The gas seeps upward from volcanic sources deep below the lake bed, gathering patiently until balance is disturbed. When it escapes, it does so without sound, swift and unforgiving. Elsewhere, the ground itself can suddenly vanish. Beneath many landscapes, hidden cavities form as underground water slowly dissolves limestone or salt. Over time, these empty spaces grow larger unseen. When the roof of such a chamber collapses, the surface above can chip away in seconds, opening a sinkhole. Some sinkholes are small and fleeting. Others are vast, swallowing roads, trees, and buildings without warning. Heavy rain often triggers these collapses as water seeps deeper into cracks and weakens the layers below. In many places, homes and cities stand above these fragile foundations, unaware of the hollows beneath. Scientists now use radar and ground sensors to map vulnerable regions, listening for the quiet signals of collapse before it happens. Though dramatic sinkholes are part of Earth's slow recycling of stone, water patient and persistent shapes the land from below grain by grain. Each collapse reveals the delicate balance between what appears solid and the hidden spaces quietly forming beneath our feet. In regions shaped by limestone, entire landscapes hide secret rivers flowing through stone. Rainwater, slightly acidic, seeps into fractures and slowly carves winding tunnels, caverns, and underground streams. These karst landscapes form vast hidden worlds beneath forests and fields where water travels in darkness long before emerging again as springs. Beneath the surface, Earth is never still. It flows, dissolves, releases, and rebuilds quietly, endlessly, even as you rest. These hidden underground networks can stretch for hundreds of kilometers, carrying entire rivers beneath the surface of the land. Above them, the ground may slowly sag or suddenly collapse, forming sinkholes, valleys, and sharp ridges that define karst terrain. A stream that vanishes into a dark cave entrance can reappear far away as a clear, cold spring, as if the earth itself were breathing water in and out. Within these lightless passages, unique ecosystems have evolved. Blind fish drift through silent currents. Pale insects move without eyes, guided by touch and vibration alone. Karst regions exist on every continent and supply drinking water to millions of people, yet their hidden nature also makes them fragile. Pollutants can travel quickly through these underground channels, spreading unseen. Exploring karst landscapes is like stepping into the planet's circulatory system, where stone and water move together in a quiet exchange, dissolving, reshaping, and renewing the surface of the earth drop by drop. Inside limestone caves, delicate structures slowly take form. From the ceiling, mineral-rich water drips steadily each drop, leaving behind a microscopic trace of calcite as it evaporates. Over centuries, these traces lengthen downward into slender stalactites on the cave floor, where the drops fall, matching mounds rise upward as stalagmites. Given enough time, the two can meet, joining into solid pillars that appear to support the cavern itself. This growth happens at a pace almost beyond perception. Millimeters may take hundreds of years to form. By lantern or headlamp, their surfaces glimmer softly, resembling frozen waterfalls sculpted by patience alone. These formations quietly record the cave's history, capturing subtle changes in water chemistry and climate. Together, they resemble forests of stone, where every column and curve began with a single drop of rain falling through darkness, carrying the memory of the sky above and the passage of immense time. Cave formations grow far more slowly than fingernails. Their beauty is not shaped by force, but by stillness. Flowstones, crystal curtains, and mineral draperies build layer by layer as water deposits thin films of stone. A single centimeter of growth may require centuries. The speed depends on countless factors: how often water drips, the purity of dissolved minerals, and the steady temperature of the surrounding rock. Some formations still glisten wet from drops that began filtering through soil and stone decades ago. Scientists study these layers like pages in a history book, reconstructing ancient climates, tracing long forgotten droughts, floods, and shifts in rainfall. Walking through a cave is like entering a clock that measures time in minerals rather than seconds. Here, change happens slowly, quietly, and without urgency. These underground sculptures remind us that beauty does not always emerge from speed or violence. Sometimes it grows from persistence, silence, and an almost unimaginable patience that stretches far beyond a human lifetime. Some caves even develop their own internal weather. In vast underground chambers, air flows through narrow passages and wide halls, creating stable microclimates unlike anything on the surface. Temperature differences and humidity gradients generate gentle winds, drifting fogs, and in rare cases, thin clouds that form and dissolve in the darkness. Deep below the ground, the earth continues its quiet processes. Water moves, air circulates, stone grows, and while the surface world rushes forward, these hidden spaces remain calm, steady, and timeless, patiently shaping the planet even as you rest. Warm air rising from deeper chambers slowly meets cooler air near cave entrances, creating gentle currents that move like miniature weather systems. In some cave networks, this exchange happens with remarkable regularity. During winter, warm air flows outward. In summer, cooler air is drawn inward. The cave seems to breathe. As surface conditions shift, moisture condenses on stone walls, forming droplets that fall steadily to the floor. These slow drips sustain fragile mineral formations and support ecosystems that exist nowhere else. To step inside such a cave is to feel the earth inhale and exhale, air, rock, and water moving together in quiet rhythm. These hidden climates preserve fossils, ancient artifacts, and rare species unable to survive on the surface. Within their stone lungs, caves remind us that even the most solid parts of the planet are alive with motion, circulation, and subtle atmospheric patterns. Beneath the gentle hills of Kentucky lies the longest known cave system on Earth. Mammoth Cave stretches for more than 400 miles underground, and explorers continue to discover new passages even today. Over millions of years, ancient rivers dissolved limestone layer by layer, carving tunnels that branch, loop, and reconnect into a vast underground maze. Inside, explorers pass through narrow corridors, enormous chambers, and winding rivers that still shape the rock in darkness. The air is cool and steady. The silence feels almost physical, as if the cave itself were listening. Its scale defies imagination, revealing how much of the planet exists beyond sight, hidden beneath our feet. Mammoth Cave is more than a geological curiosity. It is a living archive of time, shaped by water's patience into a cathedral of stone that extends far beyond the reach of light. Earthquakes can even alter the length of a day, when a massive quake redistributes the planet's mass. Earth's rotation changes ever so slightly. The effect is tiny, often measured in microseconds, but it is real. Just as a spinning skater accelerates by pulling their arms inward, the planet responds to shifts in its internal balance. After the powerful 2004 Sumatra earthquake, scientists calculated that Earth's day became fractionally shorter. The quake also nudged the position of the poles and subtly reshaped the planet. These changes remind us that time itself is influenced by the movement of rock and gravity. A single earthquake is not only a surface event, but a planetary one, quietly adjusting the rhythm of the world. The energy released by the largest earthquakes travels far beyond the fault where they begin. Seismic waves surge outward through crust and mantle, circling the globe like vibrations through a bell. Sensitive instruments can detect these waves passing through the planet multiple times before they finally fade. During the strongest events, the entire Earth flexes slightly as energy moves from one side of the globe to the other. Even regions thousands of kilometers away can register faint tremors. These distant echoes reveal a profound truth. The planet is deeply connected within itself. When one part moves, the whole world listens. Scientists use these worldwide reverberations to peer deep inside the planet. As seismic waves travel through Earth, they bend slow and reflect depending on the material they pass through. By tracking these subtle changes, researchers can map the hidden layers of the planet, revealing where rock is solid, where it flows, and how heat circulates far below the surface. For a brief moment after a major quake, the entire Earth behaves like a single instrument, vibrating gently with its own internal rhythm. Each tremor carries information from depths we will never reach, turning destruction at the surface into knowledge about the planet's inner design. Some earthquakes release energy on an almost unimaginable scale. When the largest faults rupture, the energy unleashed can rival millions of tons of TNT detonating at once. The shaking we feel is only a small fraction of that force. Most of the energy travels deep underground, shifting vast slabs of rock heavier than entire mountain ranges. To measure these enormous releases, scientists use the moment magnitude scale, which captures the true size of a quake more accurately than older systems. During the 2011 Tohoku earthquake in Japan, the energy released was so great that it slightly altered Earth's rotation and moved parts of the seafloor by several meters. Numbers like these are difficult to comprehend, yet each earthquake is a reminder that the crust beneath us is never at rest. It is constantly storing stress and releasing it in slow, powerful pulses that shape oceans, mountains, and coastlines over immense spans of time. Deep underground rock can behave more like soft putty than solid stone. At extreme depths, where heat and pressure rise far beyond everyday experience, rock no longer fractures easily. Instead, it deforms. It stretches, folds, and flows at a pace so slow we can only detect it over millions of years. This gradual movement allows mountain belts to rise, bend, and eventually sink back into the planet. Minerals twist and elongate, forming the swirling patterns seen in metamorphic rocks that later emerge at the surface. In laboratory experiments, scientists have observed heated rock samples bending rather than breaking, showing that time and pressure fundamentally change how matter behaves. The mantle beneath our feet moves this way continuously. Its slow circulation drives the drifting of continents above, carrying land masses across the planet like passengers on an unseen current. What feels rigid and permanent is in truth quietly in motion. Metamorphic rocks preserve this hidden history of heat and pressure. When rocks are buried deep within the crust, they are transformed without fully melting. Their minerals rearrange, forming new textures that tell the story of their journey. Granite can become gneiss. Limestone can turn into marble. Shale can transform into slate. Each metamorphic rock is a page in Earth's internal diary, recording how deeply it was buried, how hot it became, and how strongly it was compressed. To hold such a stone is to touch the memory of immense forces at work. It is a reminder that the planet reshapes itself not only through fire and fracture, but also through slow, patient pressure acting in darkness far below the world we see. Scientists can read these stone records to reconstruct ancient mountain building events and determine how deep certain rocks were once buried. In some metamorphic formations, the alignment of minerals even points in the direction tectonic plates once moved. These internal patterns act like arrows frozen in crystal, guiding geologists through episodes of collision compression and uplift that occurred hundreds of millions of years ago. When tectonic forces eventually raise these rocks back to the surface, we are given a rare glimpse into Earth's interior past. What appears as a quiet outcrop or polished stone once endured immense heat and pressure deep below the crust. These rocks remember that journey. Their folds and textures preserve the invisible energies that continue to flow beneath our feet, reminding us that every mountain began its life hidden, slowly rewritten by time, pressure, and heat. Slate, for example, began as nothing more than soft mud. Long ago, fine sediments settled gently on the floors of ancient seas, drifting down through still water. As layer after layer accumulated above them, the growing weight squeezed out water and compressed the mud. Heat and pressure slowly aligned the clay minerals into thin, flat sheets, transforming soft sediment into solid slate. The result is a rock so finely layered it can be split into smooth, durable tiles. This transformation tells a quiet story of patience becoming strength. What once formed the seafloor now roofs houses and lines pathways, carrying the memory of ancient oceans into daily human life. When you tilt a piece of slate toward the light, a subtle sheen appears, caused by tightly packed minerals. It is a faint echo of clay particles that once floated freely through seawater, showing how even the softest material can become strong through time alone. Marble has an equally remarkable origin. Before it gleamed in temples or sculptures, it began as limestone on the ocean floor. That limestone formed from the accumulated shells and skeletons of marine organisms, coral plankton, and mollusks compressed over millions of years. When buried deep within the earth, heat and pressure caused the rock's crystals to grow and interlock, erasing visible fossils and creating marble's smooth, luminous texture. Trace minerals introduced color during this transformation. Iron produced warm reds, serpentine added green tones, and carbon created soft grays. When polished, these crystals reflect light in a way that makes marble seem almost alive. Ancient civilizations valued it for this glow, believing it captured sunlight within stone. In reality, marble is the transformed remains of ancient seas shaped by life, burial, and geological change. Every marble column or statue is a fragment of ocean history made permanent. Gemstones carry similarly precise stories of their creation. Deep within the crust, specific combinations of heat pressure and chemistry allow crystals to form. Diamonds grow under extreme forces hundreds of kilometers below the surface. Emeralds develop in mineral rich veins where hot water moves through fractured rock, carrying elements into perfect alignment. Rubies, sapphires, topaz, and quartz each require their own narrow set of conditions rarely met in nature. This rarity is what makes gemstones precious. Their beauty comes from atomic order formed under extraordinary circumstances. When cut and polished, their clarity reveals structures built one atom at a time, showing how stability can emerge from intense pressure and heat. Before reaching human hands, these stones travel long paths lifted by volcanic eruptions, exposed by erosion, and shaped by time itself. Every gemstone is a small geological biography, a record of deep processes brought slowly to the surface. Holding one is holding a fragment of Earth's hidden interior, transformed patiently and delivered across millions of years. Each gemstone is a messenger from a different environment within the planet, carrying a record of hidden processes that unfolded far below the surface. To look into a gemstone is to look backward into Earth's memory, where immense pressure worked patiently and crystallization followed precise physical laws. Every facet reflects the quiet discipline of atoms, arranging themselves over vast stretches of time, turning invisible forces into glittering symmetry. Rubies and sapphires appear completely different at first glance, yet they are made of the same mineral corundum. In its pure form, corundum is colorless, composed only of aluminum and oxygen locked into a tightly packed crystal lattice. When trace amounts of chromium enter that structure, the crystal absorbs and reflects light differently, producing the deep red glow we call ruby. When iron and titanium replace those atoms, instead, the result is blue sapphire. Other trace elements create yellow green or pink varieties. These tiny atomic substitutions alter how light moves through the crystal, transforming a single mineral into a spectrum of colors. The fact that two of the world's most prized gemstones share the same chemical foundation shows how subtle changes at the atomic scale can produce extraordinary beauty. Each color is a chemical fingerprint proof that nature's artistry begins with invisible interactions deep within the earth. Emeralds form under some of the rarest conditions found in geology. Their creation requires an unusual meeting between silica rich rocks and beryllium bearing fluids environments that almost never overlap. When tectonic forces bring these ingredients together, the mineral beryl can form tinted green by traces of chromium or vanadium. This delicate balance occurs only in specific mountain regions shaped by intense geological activity. Most emeralds contain tiny fractures and inclusions, often called gardens, that formed as the crystal grew under stress. These features are not flaws, but evidence of a natural origin, marks left behind by pressure, heat, and shifting fluids. To hold an emerald is to hold the result of improbable chemistry and immense patience, a stone that carries the tension of its birth within every shimmering surface. Opal forms in an entirely different way. Unlike most gemstones, it is not crystalline. Opal develops when groundwater rich in dissolved silica seeps through rock and slowly deposits microscopic spheres of silica. Over time, these spheres stack into ordered layers. When light enters the stone, it bends and scatters between them, producing the shifting rainbow colors known as play of color. Many opal deposits formed in landscapes that were once wet but are now dry. As ancient water evaporated, it left behind these glowing structures locked in stone. Under magnification, opal reveals remarkable internal order hidden within what appears chaotic to the naked eye. Australia's famous opals formed in an ancient inland sea, capturing the memory of vanished rivers and rainfall. Each opal preserves not only light, but the quiet history of water moving through rock long ago. Meteorites found on Earth carry stories from before our planet existed. These fragments of rock formed billions of years ago from the same cloud of dust and gas that gave rise to the sun and planets. Many contain minerals that have remained unchanged since the earliest days of the solar system, preserving ancient chemical conditions frozen in time. By studying meteorites, scientists learn how planetary building blocks assembled, melted, and separated into cores and crusts. Some meteorites even contain organic compounds, suggesting that the ingredients for life were already present in space before Earth formed. To hold a meteorite is to touch material older than our world itself, a traveler that crossed unimaginable distances to arrive in human hands. Within certain meteorites, scientists have discovered microscopic grains known as presolar dust. These tiny crystals formed in the outer layers of dying stars long before the sun was born. Carried into space by stellar winds, they survived the violent birth of the solar system and became embedded in meteorites. These grains are older than Earth, older than the planets, and older than the sun itself. They are fragments of ancient stars, preserved against all odds. In them, geology and astronomy meet, reminding us that the story of stone does not begin on Earth, but among stars that lived and died long before our planet took shape. Over billions of years, these ancient grains drifted through the Milky Way, carried by interstellar clouds, until they became part of the material that formed our solar system. Their isotopic signatures reveal origins unlike anything naturally produced on Earth, confirming that they were forged in stars that lived and died before the sun existed. Finding such particles inside a meteorite is like uncovering untouched stardust matter that predates planets, oceans, and life itself. When scientists analyze these grains, they are reading records written before sunrise ever touched Earth. Each one carries evidence of supernova explosions and the slow expansion of red giant stars. They remind us that our planet did not form in isolation, but from recycled stellar material. Earth itself is the descendant of earlier stars, shaped from the ashes of long extinguished suns. Rocks brought back from the moon have helped scientists determine the age of Earth's earliest crust. The samples collected during the Apollo missions revealed more than lunar history. Their chemical and isotopic makeup closely matches that of Earth's mantle, supporting the idea that the moon formed after a massive collision between the early Earth and another planet-sized body. Debris from that impact eventually gathered to form the moon. By studying these rocks, scientists were able to estimate when Earth's crust first solidified roughly 4.5 billion years ago. Some lunar basalts also preserve evidence of intense meteor bombardment during the early solar system, a record erased on Earth by erosion and plate tectonics. The moon, geologically quiet for billions of years, kept a memory our planet could not. Each lunar sample is a shared chapter of two worlds born from the same violent beginning. The oldest minerals ever discovered on Earth are tiny zircon crystals found in ancient Australian rocks. These microscopic grains formed more than 4 billion years ago, shortly after the planet itself took shape. Zircons are remarkably durable, surviving erosion, burial, and extreme heat that destroyed most early crustal material. Inside each zircon is a trace amount of uranium that slowly decays into lead at a known rate, allowing scientists to measure its age with, with extraordinary precision. Even more remarkable, their chemical composition shows signs of interaction with liquid water. This suggests that Earth cooled rapidly after its formation, developing oceans far earlier than once believed. Before these discoveries, scientists thought the early Earth remained a molten surface for hundreds of millions of years. Zircon evidence changed that view. It revealed that rain rivers and oceans may have existed within just a few 100 million years of Earth's birth. Each zircon, smaller than a grain of sand, is a time capsule preserving the moment water first touched solid ground. Through these crystals, we glimpse a young world where steam condensed clouds formed and the first rain fell onto cooling rock. They mark the beginning of the blue planet long before continents stabilized or life emerged, a record of Earth becoming habitable far sooner than expected. In Earth's earliest chapters, vast regions of the continents were buried beneath immense lava fields, stretching across areas the size of modern countries. As heat escaped from the young planet's interior, molten rock poured across the surface again and again, reshaping the crust in sweeping volcanic episodes. These ancient lava plains hardened into thick layers of basalt, forming the foundation upon which later continents would grow. Those fiery landscapes eventually cooled, fractured, and were reshaped by water, wind, and tectonic motion. But deep within them, the memory of that molten past remains locked into crystal structures and mineral chemistry. The continents we walk on today carry the scars and signatures of a time when Earth was still learning how to be solid. And as you rest now, the planet continues its slow transformation. Heat still rises, rock still flows, water still cycles through stone. The story of geology is not finished. It unfolds quietly beneath you, written not in moments or years, but in patience measured by millions of breaths of the earth itself. Across deep geological time, Earth has experienced immense volcanic episodes known as flood basalt eruptions. During these rare events, vast regions of the planet were submerged beneath layer after layer of molten rock. Instead of brief explosions, these eruptions unfolded slowly, sometimes lasting for hundreds of thousands to millions of years. Rivers of lava spread outward, forming plateaus thousands of meters thick and covering areas larger than entire modern nations. The Deccan traps of India and the Siberian traps of Russia stand as monumental remains of these ancient outpourings. When the lava finally cooled, it solidified into stepped landscapes of dark basalt. Over time, weathering transformed these rocks into mineral rich soils that continue to support agriculture today. To stand upon these regions is to stand on frozen fire, on stone that once flowed across the land, reshaping continents in silence. These vast basalt fields remind us that the calm surface of the present world conceals a far more violent past. There were ages when entire regions pulsed with magma, when the sky glowed with volcanic haze, and the ground itself seemed alive with heat. Some of these enormous eruptions did more than reshape the land. They altered the course of life itself. The gases released during flood basalt events, carbon dioxide, sulfur dioxide, and other compounds poisoned the atmosphere, darkened the skies, and disrupted climate on a global scale. Around 250 million years ago, eruptions associated with the Siberian traps coincided with the greatest mass extinction Earth has ever known. Vast numbers of marine species vanished along with much of life on land. Acid rain fell, oceans lost oxygen, temperatures rose sharply, entire ecosystems unraveled. Yet even after such devastation, life slowly returned. New species emerged, adapted, and flourished in the transformed world. These cycles of destruction and renewal are woven deeply into Earth's history. Each extinction becomes a turning point, clearing space for evolution to explore new paths. In the quiet aftermath, life begins again, reshaped by fire and time. Even today, traces of these ancient eruptions remain hidden beneath our feet. Thin layers of volcanic ash lie preserved within soils and sediments across the globe. These layers are silent records of distant eruptions, some thousands, others millions of years old. Each carries a unique chemical signature, allowing scientists to match ash found far apart and reconstruct precise timelines of Earth's past. In many regions, people unknowingly cultivate land enriched by this ancient fire. Volcanic ash breaks down into soils rich in nutrients, making areas such as Italy, Japan, Iceland, and parts of Southeast Asia remarkably fertile. To dig into such ground is to touch history itself, the remnants of catastrophe transformed into nourishment. Ash that once dimmed the sun now feeds forests and crops, completing a cycle in which destruction becomes the foundation for growth. The Atlantic Ocean itself began as part of this slow, powerful story. Long before waves filled its basin, Africa and the Americas were joined together within a single supercontinent. Around 200 million years ago, deep fractures opened between them. The crust stretched and thinned, forming a long rift valley, scarred by faults and rising magma. As the continents continued to pull apart, water flooded into the widening gap. Volcanic activity built new crust along the fracture, and over millions of years, a new ocean took shape. What is now the Atlantic began as a narrow wound in the planet's surface. Ancient rift valleys, like those still visible in East Africa today, offer a glimpse of this early stage, long depressions where the crust is slowly tearing, as it once did, between the Americas and Africa. At the center of the Atlantic, the process continues. Hidden beneath the waves lies the Mid-Atlantic Ridge, a vast underwater mountain chain where new crust is constantly being born. Molten rock rises through cracks, cools, and spreads outward in both directions. As it does, the continents on either side drift farther apart, carried along by the slow movement of the seafloor itself. Within this newly formed rock, magnetic minerals align with Earth's magnetic field as they cool. Over time, as the planet's magnetic poles reverse these alignments, create symmetrical stripes on the ocean floor. By reading these magnetic patterns, scientists confirmed that the seafloor spreads outward like a conveyor belt, providing powerful evidence for plate tectonics. The ocean continues to grow centimeter by centimeter year by year, a reminder that even the largest features on our planet are born from quiet, persistent motion. Beneath the calm surface of the sea, the Earth continues its slow unfolding, building worlds from fractures and shaping the future while we sleep. The process continues at a pace of only a few centimeters each year, so slow it escapes human notice, yet so persistent it reshapes the planet. This hidden conveyor beneath the ocean steadily widens the seas, while elsewhere older crust sinks back into the mantle at subduction zones. Creation and destruction remain perfectly balanced, keeping Earth's surface in constant quiet motion. Along these underwater boundaries, hydrothermal vents rise from the ocean floor like gateways to another world. Seawater seeps down through fractures in the crust, sinking deep until it encounters molten rock. There it is, heated to extreme temperatures, dissolving metals and minerals before rising again toward the surface. When this superheated fluid bursts into the cold ocean, it cools instantly, releasing dark clouds of minerals that billow upward like smoke. These structures, known as black smokers, form tall chimneys of iron, sulfur, and other compounds, continuously growing, collapsing, and rebuilding in the darkness. Around them, the water shimmers faintly with suspended particles, and an unexpected abundance of life gathers. In a place without sunlight, entire ecosystems flourish, feeding not on light, but on chemistry. Each vent becomes a self-contained world, a reminder that even in the deepest darkness, the planet finds ways to release energy and sustain life. Far below the reach of the sun, dense communities of organisms cluster around these vents. Instead of photosynthesis, life here relies on chemosynthesis, a process in which bacteria use chemical energy from sulfur and methane to produce food. Giant tube worms, clams, crabs, and strange fish all depend on these microbes forming ecosystems unlike anything found at the surface. Within just a few meters, temperatures can shift from near freezing to more than 300 degrees Celsius. Yet life adapts and thrives. The discovery of these deep-sea ecosystems in the 1970s transformed our understanding of biology. It revealed that sunlight is not a requirement for life, only energy, water, and chemistry. This realization expanded the search for life beyond Earth, suggesting that similar environments might exist beneath the icy shells of moons like Europa and Enceladus. What was once believed to be a barren ocean floor is now known to be alive with motion heat and quiet biological complexity. Over time, minerals carried by the vent fluids accumulate into towering chimneys, some growing taller than houses. Layer by layer, metallic compounds solidify into intricate columns that resemble stone cathedrals rising from the seabed. Some structures collapse under their own weight, only for new ones to form in their place. Within these chimneys, valuable ores concentrate similar to those humans mine on land, while their surfaces host dense microbial communities adapted to extreme heat and chemical gradients. These vents pulse gently, like underwater volcanoes breathing in the dark. They stand as proof that even in the most extreme environments, Earth continues to sculpt structure and complexity from pressure and heat, creating elaborate formations that remain hidden from almost all eyes. Above and below these processes, another invisible force quietly shapes the planet. Earth's magnetic field has reversed many times throughout its history. The magnetic poles have flipped repeatedly, with north and south exchanging places at irregular intervals. Sometimes these reversals are separated by hundreds of thousands of years, sometimes by millions, leaving their signature locked into cooling rock across the seafloor and continents alike. This magnetic memory written into stone allows scientists to trace the movement of plates, the spreading of oceans, and the long rhythm of planetary change. Together, heat motion, magnetism, and time weave a story of a world that is never still, always reshaping itself, slowly, patiently, and without pause. The cause of these magnetic reversals lies deep within Earth's molten outer core, where vast currents of liquid iron slowly swirl and flow. These moving metals act like a giant generator, producing the magnetic field that surrounds the planet. As the currents shift and reorganize, the field weakens fragments and eventually rebuilds itself in the opposite direction. The evidence of this process is written clearly into volcanic rock on the ocean floor. As lava rises, cools, and hardens, tiny iron minerals inside it align with the magnetic field at that moment. When the field later reverses, newly formed rock locks in the opposite orientation. Over millions of years, this creates symmetrical policy bands of alternating magnetic polarity spreading outward from mid-ocean ridges. Each stripe marks a chapter in Earth's long magnetic history. Although a full magnetic reversal may take thousands of years to complete, life has endured every one of them. Forests grew, oceans flowed, and evolution continued uninterrupted. These events remind us that even the invisible shield protecting Earth from cosmic radiation is not static, but alive, shaped by the restless motion of the planet's molten heart. During a reversal, a compass would not suddenly flip overnight. Instead, it would slowly lose its certainty. Over centuries, magnetic north would drift away from its familiar position, wandering toward the equator and eventually pointing roughly south. At times, the field might split into multiple weak poles before settling into its reversed state. Rocks preserve the memory of these changes. Their magnetic minerals remain frozen in the direction that was north when they formed, allowing scientists to reconstruct the long wandering paths of Earth's magnetic poles. Though the idea may sound unsettling, Reversals are a natural part of planetary behavior. They have never triggered mass extinctions or atmospheric collapse. Instead, they reveal the vitality of the geodynamo, the deep, unseen engine that has kept our Earth's magnetic heart beating for billions of years. Even today, the magnetic poles are not still. Earth's magnetic field continues to shift and drift. The North Magnetic Pole, once located in the Canadian Arctic, is now moving steadily toward Siberia at a pace of tens of kilometers per year. This motion reflects subtle changes in the flow of molten iron far beneath the surface. Satellites constantly monitor these movements, updating navigation systems that depend on magnetic reference points. While magnetic north wanders geographic north, the axis around which the planet spins remains fixed. The distinction is invisible to most of us, but to scientists it is a quiet signal of deep planetary motion. The same invisible force that guides a compass needle also reveals the slow liquid heartbeat of the world beneath our feet. Above it all of this motion, another celestial presence quietly shapes Earth's long-term stability. The moon plays a crucial role in steadying the planet's axial tilt. Without its gravitational influence, Earth's orientation could wobble chaotically over time, swinging from nearly upright to dramatically tilted. Such instability would drive extreme climate shifts, transforming polar ice into tropical seas and then reversing again. The moon's steady pull keeps Earth's tilt within a narrow, gentle range. This stability has allowed long-term geological processes to unfold and life to evolve without constant upheaval. Ocean currents, ice ages, and weather patterns all depend on this quiet balance. In this way, the moon does more than light our nights. It helps hold the planet steady, allowing Earth's deep rhythms, magnetic, geological, and biological, to continue their slow, graceful dance across time. The gravitational pull of the moon does more than move the oceans back and forth. Through the tides, it quietly redistributes energy across the planet's surface, influencing erosion, sediment transport, and the slow reshaping of coastlines. Much of Earth's geological stability, its balance between steady order and gradual change, owes itself to this silent companion circling above. Every gentle tide, every repeating season carries the influence of the moon. For more than 4 billion years, it has guided Earth's rhythms without interruption. Its presence has softened extremes, moderated motion, and helped shape a world where change unfolds slowly enough for life to adapt. As the moon's gravity pulls on Earth's oceans each day, the water rises and falls in a predictable rhythm. Over long stretches of time, this motion becomes a powerful geological force. Tides carve estuaries, widen bays, and transport vast amounts of sand and sediment that build beaches, mudflats, and river deltas. Along rocky shores, repeated tidal action wears down cliffs, grain by grain, while in shallow waters, it spreads nutrients that sustain rich marine ecosystems. In some parts of the world, the difference between low tide and high tide can exceed 10 meters. These regions create wide intertidal zones that shift daily between land and sea. Such environments are among the most productive on Earth, serving as nurseries for fish feeding grounds, for birds and homes for countless small organisms adapted to constant change. Across geological time, tidal forces have helped shape continental shelves and barrier islands influencing how coastlines evolve and how oceans interact with land. The shoreline we see today is not fixed. It is a moving boundary sculpted patiently by the moon's distant pull, reshaped grain by grain through cycles too slow to notice in a single lifetime. Far beneath warm tropical waters, another quiet partnership between geology and life is at work. Coral reefs, vibrant with living creatures, are also massive geological structures built from calcium carbonate. Each individual coral polyp secretes a tiny limestone skeleton. Over generations, these skeletons accumulate, stacking upward toward sunlight. Over thousands and millions of years, this slow construction creates reefs so large they can be seen from space. The Great Barrier Reef stretches for more than 2,000 kilometers, formed not by sudden events, but by continuous growth across deep time. As older corals die, new ones grow upon their remains, preserving the structure and extending it upward. These reefs act as natural breakwaters, absorbing wave energy and protecting coastlines from erosion. At the same time, they serve as detailed records of ocean history. Their layers preserve information about water temperature, chemistry, and sea level, allowing scientists to read the story of ancient climates locked within stone, built by living organisms. Even fossilized coral reefs tell of oceans that once covered lands now dry. Some reefs growing today began tens of millions of years ago, making them older than many mountain ranges on land. They are living geology structures that breathe, grow, and change quietly, recording the long dialogue between sea stone and time. In the slow rise and fall of tides, and in the patient growth of coral, we see the same pattern repeated again and again. Change guided not by violence, but by rhythm, not by speed, but by persistence. A reminder that much of Earth's greatest shaping happens gently under the steady influence of forces that never sleep. Some coral reefs began forming while dinosaurs still walked across the land. Over immense spans of geological time, mountain ranges have risen and worn away, oceans have advanced and retreated, yet beneath the sea, these living structures continued their slow expansion. At their core, reefs are built from compacted limestone created by the accumulated skeletons of countless microscopic organisms. As sea levels shifted, reefs adapted. When the water deepened, they grew upward toward the light. When shorelines migrated, they followed, adjusting their position over thousands of years. Today, the fossil remains of ancient reefs can be found in deserts and high on mountain slopes. Silent evidence that regions once submerged beneath warm seas are now dry land. The persistence of coral reefs reflects the planet's continuity through upheaval. Their layered skeletons record both biological growth and geological change. Each reef stands as a living structure shaped by time, older than cities, older than civilizations, and in some cases older than the mountains themselves. Across the planet, materials shaped in one environment often sustain life in another. Fine mineral dust lifted from vast deserts can travel enormous distances through the atmosphere, carried by high altitude winds across oceans and continents. Eventually, these particles settle onto distant ecosystems, delivering essential nutrients where they are needed most. The Amazon rainforest, for example, relies on phosphorus rich dust carried from the Sahara Desert to replenish its soils. Heavy tropical rains would otherwise wash these nutrients away. Satellite images reveal immense plumes of dust crossing the Atlantic, glowing faintly in sunlight before dispersing invisibly into forest canopies. Each grain is a geological voyager, leaving one landscape to nourish another. In this quiet global exchange, deserts and rainforests are linked, joined by wind erosion and the slow circulation of Earth's materials. Deep within certain rocks, both from space and from Earth itself, lie fragments far older than our planet. Microscopic grains preserved inside meteorites and ancient terrestrial rocks were formed in dying stars long before the solar system existed. These tiny particles survived the collapse of the cloud that created the sun, eventually becoming embedded in the material that formed planets. Their atomic signatures are distinct from anything naturally produced on Earth. By studying them, scientists trace stellar life cycles from slow burning red giants to explosive supernovae. Each grain carries atoms forged in cosmic furnaces, reminding us that Earth's geology is inseparable from the wider universe. The ground beneath us contains not only the history of our planet, but echoes of stars that lived and died long before Earth took shape. Some of the most valuable elements we mine today also arrived from space. During Earth's early formation, heavy metals such as gold and platinum sank deep into the molten core. The deposits found near the surface today were delivered later during a period of intense meteor bombardment more than 4 billion years ago. Asteroids rich in these elements collided with the young planet, scattering their contents across the crust. Every vein of gold or platinum is a remnant of that ancient cosmic rainfall. These metals were forged in stellar explosions, traveled through space, and became embedded in Earth through violent impacts. To hold gold in your hand is to touch a fragment of that distant past where celestial destruction gave rise to earthly beauty. It is a quiet connection between the violence of the early solar system and the calm permanence of stone. Over time, even the marks of these impacts can fade. Some ancient craters have been softened so completely by erosion, tectonic movement, and sediment that they are barely visible today. Only subtle, circular patterns or faint anomalies in rock layers reveal where colossal forces once struck the surface. These hidden scars remind us that Earth is constantly rewriting its own history, smoothing even the most dramatic events into the slow continuity of geological time. Over immense spans of time, wind, water, and the slow motion of tectonic plates can almost completely erase the evidence of a meteor strike. What begins as a vast circular wound in the crust is gradually softened. Sediment fills the basin forests, take root, oceans advance and retreat, and the sharp rim fades into gentle hills. From the surface, the land appears ordinary again, yet beneath it, the memory remains. Hidden in the rocks are unmistakable signatures of impact. Shattered quartz crystals, minerals melted, and re-solidified in an instant, and deep rings of fractured crust all point to a moment of extraordinary violence. Using satellite imagery, gravity measurements, and magnetic surveys, scientists have learned how to reveal these buried scars. Many ancient craters were later filled by lakes towns or entire cities whose inhabitants never realized they lived atop a cosmic footprint. Across North America, Africa, and Australia, impacts billions of years old lie concealed beneath younger layers of stone. Their near invisibility shows how thoroughly the planet heals itself, smoothing even catastrophic wounds until they blend seamlessly into the surrounding world. Some of these ancient collisions may have altered the course of life itself. Around 200 million years ago, a massive asteroid is thought to have struck near what is now Canada close in time to a major extinction at the end of the Triassic period. The impact would have unleashed unimaginable energy, darkening skies with debris, igniting fires across vast regions, and disrupting climate systems worldwide. In the turbulent aftermath, volcanic activity intensified and temperatures swung sharply. Many reptile groups declined, unable to adapt to the rapidly changing environment. Dinosaurs, however, proved more resilient. They diversified, spread, and eventually rose to dominate the land. The crater left behind, though, deeply eroded, still preserves traces of molten rock and shock-altered minerals, quiet evidence of a moment that reshaped evolution. Again and again, impacts like this have reset the biological balance, closing some branches of life while opening space for others to flourish. But not all cosmic encounters cleared the way for growth. Some brought endings on a far greater scale. 66 million years ago, an asteroid roughly 10 kilometers wide struck the shallow seas near today's Yucatan Peninsula. The energy released rivaled billions of nuclear explosions combined. Rock was vaporized, shock waves raced around the globe, and fires swept across continents as debris rained from the sky. Dust and aerosols filled the atmosphere, blocking sunlight for years. Photosynthesis faltered. Food webs collapsed. More than 70% of all species disappeared, including the non-avian dinosaurs that had ruled the planet for over 160 million years. In silence and darkness, one age ended, preparing the ground for another chapter of life to begin. The crater it left behind, known as Chicxulub, still rests beneath thick layers of limestone on the Yucatan Peninsula. Though hidden from view, its circular form remains astonishingly intact. Beneath its buried rim, rocks bear the unmistakable signatures of extreme heat and crushing pressure, a silent archive of one of the most violent moments in Earth's history. Yet from that devastation came renewal. The extinction that erased the age of dinosaurs opened space for mammals to expand, adapt, and eventually give rise to humans. What ended one chapter made room for another to begin. This cycle of loss and emergence reveals a deep truth of our planet. Destruction and creation are not opposites, but partners in Earth's endless rhythm of change. The surface of the planet is scattered with countless scars from ancient cosmic collisions. Some craters remain visible as vast circular depressions, while many more lie concealed beneath ocean's deserts and younger layers of rock. Geologists uncover them by reading subtle distortions in gravity and magnetism, faint circular patterns that betray structures buried far below. Some of these hidden impacts date back to Earth's earliest eras when the young planet endured an intense barrage of asteroids and comets. Those collisions reshaped the crust and may have delivered water, carbon, and other ingredients essential for life. Though erosion and plate motion have erased their surface traces, the memory of these events remains locked within the stone. Each newly discovered crater is a reminder that the calm world we inhabit was forged through unimaginable violence during its cosmic youth. Even now, Earth continues to receive material from space. Each day, hundreds of tons of microscopic cosmic dust drift into the atmosphere. Most of it arrives quietly glowing for an instant, as meteors or settling unnoticed onto land and sea. These particles come from comets and asteroids, shedding fragments as they circle the sun. Scientists have collected this interplanetary dust from Antarctic ice rooftops and remote landscapes. Under microscopes, the grains reveal smooth metallic spheres formed as they melted during their fiery descent. Over billions of years, this steady accumulation has subtly added to Earth's mass even as erosion and escaping gases remove material elsewhere. It is a gentle exchange between planet and cosmos, a constant silent rain of star-born matter reminding us that Earth is never truly isolated. Geology ties every mountain, ocean, fossil, and living organism into a single, continuous story. The forces that raise peaks also carve valleys, circulate oceans, and create the conditions for life to emerge and evolve. Fossils record how shifting climates and landscapes shaped living beings, while minerals preserve the deep processes that built and recycled continents. Every river carries the history of erosion. Every grain of sand was once part of solid rock. Over billions of years, plate tectonics, volcanism, and weathering have woven an unbroken narrative connecting land, life, and time. Geology is the language of that narrative, written not in words, but in layers beneath our feet. The rocks we walk upon are the planet's memory made solid. Each pebble cliff and mountain is a page in Earth's vast diary. Within their textures lie the traces of ancient oceans, blazing eruptions, advancing ice, and drifting continents. To study them is to listen to the planet, remembering itself, and to recognize that the world around us is both unimaginably old and quietly alive, still unfolding its story beneath every step we take. Radiometric clocks quietly measure the ages of rocks, while fossils and mineral patterns reveal the climates, landscapes, and lives that came before us. Stone remembers pressure and heat flood, and drought, birth, and decay. Together, these records form a vast archive of time, proof that the earth is always moving, yet endlessly patient. Standing on solid ground can feel like permanence, but in truth, we are standing on history in motion, a crust that is forever forming, breaking apart, and becoming whole again. To listen closely to the earth is to hear its long, gentle memory, the soft murmur of stone, preserving the story of a world that has never stopped changing, never stopped becoming itself. Even now, as you rest, the planet turns slowly beneath stars, that once forged the elements within your bones. Beneath the quiet surface, molten rock flows in endless cycles. Continents drift like slow clouds across a deep sea of stone. Geology teaches us that change does not always roar. Most of the time, it whispers. Mountains rise grain by grain. Oceans widen beyond the reach of memory. Every pebble, every crystal, every grain of sand carries a trace of time so vast that our own lives seem like brief flashes of light. And yet those flashes belong to the same pattern written into the same fabric of the planet itself. Somewhere deep within the earth, pressure builds. Somewhere else it eases, and a new rock begins its long transformation. Far above wind grinds stone into dust. That dust drifts across oceans, nourishing distant forests and feeding life anew. Nothing is ever lost. Everything becomes something else. The planet breathes in the slow rhythm of stone, and without realizing it, we breathe with it. You may think of the places you have walked, the crunch of gravel beneath your feet, the rough edge of a cliff, the warmth of sand slipping through your fingers. Each sensation is a story told in minerals, shaped by time and touch. The earth is not only alive at its surface, it lives within itself, turning memory into matter, silence into form. As you drift toward sleep, let this thought sink in like rain through soil. Imagine the deep, steady pulse of the planet beneath you, ancient, calm, unhurried. Let it quiet your thoughts and slow your breathing. You are part of this story too. A brief moment in a vast, unfolding world that remembers everything. If you enjoy these quiet journeys, I invite you to subscribe, or leave a gentle thought below. It helps others find their way here, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy. Let the earth cradle your thoughts, still patient, still eternal. Sleep well. Good night.